Okay guys, I'm back with the next video in the series. It's time for us to take a look at the conceptual questions that are going to be on the test. So, in all three versions of the test we have be able to define velocity and acceleration. In your own words, I will give full points to any correct definition. Okay, so there are a couple of ways we can attack this. I think the easiest way to do this is to say velocity is displacement over time, or delta x over t. Velocity is the rate at which an unmoving object clears ground, right? A high velocity means that you're moving a lot of distance in a shorter period of time. I think that defining velocity as displacement over time, or change in position, delta x over time, is the best way to define velocity. You could also define velocity as speed speed with a direction too. It's speed with a direction attached. So velocity is the same thing as speed, but it's got a direction attached, right? It cares like forward, backward, east, west, that sort of thing. Now acceleration, I would define as a change in velocity over time. We can write that as delta v over t. An acceleration is a change in velocity over time, whereas a velocity is a change in position over time. This represents moving, this represents changing the speed at which you are moving. So I would write, for acceleration, I'd say that it's speeding up, slowing down, or turning. Those three things constitute acceleration. Okay, the next one. Be able to explain the difference between displacement and distance, as well as the difference between velocity and speed. Okay, so displacement is the straight line between 2 points. You guys like how my I and my O turn into one letter? And then our distance is the path taken by an object. Here's the difference between displacement and distance. Here are my 2 points. This distance here, that is the displacement. Right, so if I've got an object and I'm starting here and I'm ending up here, my displacement is just the straight line between these 2 points. My distance, if I go like around the place, this is my distance. So distance cares about the path that I follow, this whole path of me going squiggly, squiggly, squiggly over here. My distance is counting all of this space. My displacement only cares about the straight line distance, the direct space between these 2 points. So that's the difference between displacement and distance. Displacement only cares about how far apart the 2 points are. Distance actually cares about the path taken by the object. You can go through all these squiggly little paths there. And then velocity and speed is very easy. Velocity is displacement over time, and speed is distance over time. So if, let's say, I'm walking to the grocery store or whatever, and I'm like, I take a cut through the park because it's a nice day, and I walk around and I do all this like, ooh, yada yada yada, I'm walking around, yay. My velocity is going to be a lot lower than my speed is, right? Because my velocity just cares about this distance. If that took me 20 minutes, it's going to be this distance over 20 minutes. My speed is going to be a lot higher because I get to count all of this extra space that I walked around in. So I think that's the easiest way to describe the difference between velocity and speed, as well as distance and displacement. Okay, next one. Consider an object thrown straight upwards on Earth. What is its acceleration? What is the acceleration acting at the top of that object at the top of its arc? What about its velocity? Okay, so here's my pen. throw it up, oopsie, drop it down. Right, so it's going to go like this. Excuse me. And this question here is asking, at the top here, what is the velocity and what is the acceleration? So, we know that at the top of an arc, velocity equals 0. The top part of an object's arc, the velocity is 0. It'll leave it'll leave its initial point, in this case my hand, I throw it up, right? It leads my hand with a speed, and it goes slower, 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 slower. The whole time it's inching forward while gravity is slowing it down. At the top, this represents the point where it's taking its final push forward before gravity finally makes it start falling back down again. So we go slower, 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 slower. Stopped up here for just a second. It's stopped. It's got a velocity of 0 at the top, and then faster, 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 faster as it falls down. So the velocity acting at the object at the top is 0 meters per second. The acceleration acting at the top, though, this is still in a gravitational field, and notice a second after this, a millisecond after this, it starts falling down again. So the acceleration acting on this is still 9.8 meters per second squared down. So that's how we can find it. 0 at the top, and then the acceleration at the top is going to be 9.8, the same as it is throughout the rest of this. Okay, next, let's say I throw a baseball straight up and catch it in my hand at the same height I threw it from. Explain why it hits my hand at the same speed I threw it at. Okay, so here's something that's kind of interesting. Here's my hand. Here's a baseball. Oh, geez. Don't worry about my drawing, it's fine. It goes up and comes down back into my hand. We can say my other hand at the same height, that's fine. And if we think about this, its initial velocity here is going to be equal to its final velocity down here. This, let's say this is, I don't know, 5 meters per second. This is going to be negative 5 meters per second. It's going to be the same with an opposite direction. Right? And there are a couple of ways we can think about this. The first way is through conservation of energy. We haven't talked about conservation of energy here in physics class yet. Don't worry, we will. But if you remember, energy must be conserved in science. So if I give this some speed out of my hand, when it's down to the same height, it has to have the same speed because it can't have more energy than what I released it with, right? I can't give it, like, this thing's not going to come down faster because I only gave it this much energy, only gave it the amount of energy needed to go 5 meters per second. And it's not going to come down substantially slower. It'll come down a little slower because of air resistance and stuff, but it's not going to come down much slower because I gave it this much energy, and that energy is still in the ball, right? So thinking about it from a conservation of energy perspective, that's how that works. But I think the easiest way to explain why it hits your hand at the same speed you threw it at is, consider our arc here. We start off with an initial velocity of 5 meters per second, let's say. And then it goes slower, 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 stops at the top. Faster pointing down, faster pointing down, faster pointing down, faster pointing down, faster pointing down. The amount of space that gravity has to accelerate this, right, is the same for both of these. This delta x and this delta x, the path up and the path down are the same distance, right? So all this space that gravity has to slow it down is the same amount of space that gravity has to speed it up on this side. So what that means is it goes from 5 to 0 up here, and then it goes from 0 to 5 up here. And because gravity is the same on both sides, right, because gravity is constant, that means that the speed that it's going to hit your hand with is going to be exactly the same. So I would say something along the lines, to answer this question, of gravity is constant and has the same amount of distance to both speed up and slow down the object. So think about it like this. Gravity can, let's say this is, I don't know, 2 meters or something. This is saying gravity gets 2 meters worth of space to slow this down. It then gets 2 meters worth of space to speed it up. And because gravity is the same on both sides, that means that the speed it builds up to is going to be the same speed as it left with. In real life, this is going to be a little bit lower because of air resistance and stuff. It loses some energy to the surroundings. But anyway, that's how we do that one. Not too bad. let's take a look at the next question, which involves my new friend, Mr. Nah. Mr. Nah is very cool. He's the new bio teacher. He replaced Mr. Ritchie. He's in my old room, actually. So Mr. Nah, in this problem, is driving 15 miles east to his friend's house in 20 minutes. So here is Mr. Nah. He goes 15 miles. East is this way, so it takes 20 minutes. I'm going to call this part 1. He then travels 7 more miles east to the supermarket in another 15 minutes. So here's the first part. He then, from here, we go to the second part. He goes another 7 miles in another 15 minutes. And then on his way back home, he runs out of gas 16 miles, 20 minutes after leaving the supermarket. So 15 to 7, that's 22. And then 16 over here. We're going to go backwards a little bit. I'm going to draw this down here, actually, so it doesn't overlap. So we go backwards like this. There's the third part of our journey. This is 16 miles, and this takes 20 minutes. Okay. So our first question, A, asks what the total distance he traveled was. That's pretty easy. Total distance. Remember, distance only cares about the total length. It does not care about the difference in position of points. So 15 miles plus 7 miles plus 16 miles. The whole path of 15 plus 7 plus 16 is 22, 48. So that's 48 miles. B. Our displacement. Now, with our displacement, it's still pretty easy, but we got to think about this more. In displacement, we only care about the distance between where we started and our final point here. So we're caring about this amount of space. So if we went 15 east and then here's the way we could do this. I'll call this way positive and this way negative. We could do 15 miles from the east. So it's plus 15 miles. Plus another 7 miles, because we're calling east positive. And then minus 16 miles, because we go backwards there. Right? So 15 plus 7 is 22. I went 16 this way, so I'm going to end up with a net total of positive 6 miles. Excuse me. Oh, also, I'm dumb. Excuse me. This isn't 48. This is 38. Basic addition error. Pardon me. we caught it, though. It's all good. Okay, so then C asks what was his average speed. D asks what was his average velocity. So, how we find this is pretty easy. We can go C for average speed. So speed, remember, speed is distance over time. So C is going to be distance over time. Our distance is 38. Our time is 20, 40, 55. Yeah, over 55 minutes. You can leave this in miles per minute if you want. So let's go ask my calculator what 38 divided by 55 is. We get 0.69, or 0.7. So we're going to call that 0.7 miles per minute. And then D is what's our average velocity? D, velocity, is displacement over time. So that's going to be 6 over 55. 6 miles, which is our displacement we found earlier, over 55 minutes. So 6 over 55 is going to be lower than that. 0.1. So D is going to be 0.1 miles per minute for average velocity. And there we go. That's how we do it. Not so bad. Okay, so with that, I will see you guys in the next one.